My name is Paul, and today I'm going to go through the answers of the 2024 HSC Physics paper, and in particular I'm going to be looking at the short answer section. And please remember to hit that subscribe button and to like and put a comment down below if this video ends up being helpful for you. Before we start, just one caveat. I am going to go through the questions as a full explanatory type of situation. That is, I'm going to not necessarily outline the marking guidelines as it is published by NESA. In other words, my answer may actually be more fulsome than the minimum required to get full marks. The whole purpose here is to understand the answer and to enable this to be used to consolidate a student's understanding of the topic. So let's get started. So our first question deals with the concept of torque, the magnitude of the torque. So we're not interested in the direction. The answer can be simply determined by the fact that the torque is equal to the force times the radius, or the moment, times the sine of the angle. Always write down the formula first. Now, as a result, the force is given, that's 75. We multiply that by our radius, which is 18 centimeters, remembering SI units, 0.18, and multiplied by the sine of 40. And so we're going to put this in sine 40. And you do the calculation, you're going to get 8.68 Newton meters. Part B, it says explain in two ways which torque can be increased in a simple DC motor. To do this, let's quickly look at the mathematical formula for a DC motor. That is, torque is equal to B A I N sine theta, where B is the magnetic field strength, A is the cross-sectional area of that motor, I is the current, N is the number of turns, and sine theta is the angle between the area vector and the magnetic field. Now we want to increase the torque. So in other words, when theta is equal to 90, we have the maximum torque, and as a result, all other situations will be less. So this actually does not address this situation. So we are not going to be looking at the sine theta component, which means you can talk about a number of things here. You can talk about the magnetic field strength. Now, if you have this formula, automatically you're explaining the reason, your justification. Increasing the magnetic field strength increases the torque on one side of the wire, and of course that's dependent on the magnetic field. The cross-sectional area, that is the dimensions of your loop, whether it is increasing the radius of turn or increasing the length of the wire that goes through the magnetic field. Either way, we're increasing the cross-sectional area. We can talk about increasing the current. Of course, the force is dependent on the current. And finally, every single turn multiplies the strength of the torque. And so there's your answer. Question 22, and we've got a graph on the data gathered by Hubble, shows the relationship between the recessional velocity of galaxies and their distance. It says describe the significance of this graph in our understanding of the universe. And the key is that. So the significance of the graph suggests that as distance increases, so does the recessional velocity. Now the graph obviously shows that as distance increases, what we end up getting is the velocity is increasing. But this is in all directions. Now that means, as a result, we have expansion of our universe. Now that I don't think is enough. You need to go a bit further. That means if you go backward in time, that would suggest, as a result, that we have an origin, and of course, that would lead us to the idea of the Big Bang Theory. Question B says, well, how was these recessional velocities of the galaxy determined? Well, this is all about the absorption spectra. Now, because most galaxies are made up of hydrogen, what they noticed is that the lines for hydrogen were shifted towards the red end, and so we have this idea of redshift. The further the redshift, the faster the velocity. And so therefore a greater redshift, I'll just use simple letters here, therefore the greater the velocity. And so as a result, by measuring the amount of redshift, they can determine the recessional velocity. Question 23. It's a 9-marker, but it's broken down into a number of sections. What is the first section interested in? Well, this is all about Chadwick's experiment about the discovery of the neutron. And he fired alpha particles at a beryllium surface that received unknown radiation, hit the paraffin, and then other radiation came off, which could be detected. And this is what you're being assessed on. What is the role of the paraffin? Well, in essence, paraffin is a very large carbohydrate. It has lots of hydrogen atoms. In other words, it has lots of protons. Now, the thing about protons is that they are charged, which means that you can detect them with some sort of detector that responds to the presence of charges. And so therefore, these protons were able to be detected. Now, that also means that their energy can be determined and their momentum can be determined. And so the role of the paraffin is to provide these protons as a result. Part 2, it says, well, how did Chadwick's experiment change the model of the atom? Well, this lends to what we said before. You see, if Chadwick was able to look at both the energy and the momentum of these protons that were being knocked out by this unknown radiation, he was able to establish through the application of the law of conservation of momentum and the law of conservation of energy, he could work backwards to determine the properties of this unknown radiation. And what he discovered was that, first of all, they had no charge. And secondly, they were slightly more massive than our protons. And of course, that meant he was able to identify, in this case, the unknown mass at that stage to be the neutron. There you go. And so therefore, the nucleus did not just consist of protons, but of neutrons as well. Our part B question says, explain how de Broglie's hypothesis regarding the nature of electrons addressed the limitations of the Bohr-Rutherford model of the atom. Now, when you read this for 4 marks, you need to appreciate the fact that we need to start off, well, what is the Bohr-Rutherford model? Now, you would normally write this, but I'm just going to simply do a diagram. We have a planetary model of a nucleus, which is positively charged. And of course, we have electrons in discrete orbits around that particular nucleus. Of course, it was Rutherford who established the planetary model, but Bohr suggested that they were in discrete orbits where they would not lose or gain energy. But the question de Broglie asked was, and the question that wasn't actually addressed yet by Bohr, was, well, why do they have discrete energy? And so what did de Broglie do? So when we have de Broglie, he basically surmised by using the idea of E equals HF and the fact of E equals mc squared, that basically any particle with momentum has an associated wavelength. That is, the wavelength is equal to h over p. That is, all objects with momentum have an associated de Broglie wavelength. Now, in most cases, our particles with momentum are so large that the wavelength is incredibly small, unmeasurable, in fact, and so we don't actually measure this. But when we look at electrons, well, they have a wavelength that can be detected. So he surmised, well, if they have a wavelength, they have discrete orbits if they are standing in standing waves around the actual nucleus. So in other words, they are in resonance. They're in standing waves around the nucleus, and this can only exist in certain whole numbers of wavelength as a result, and so therefore explained why they had discrete orbits. Question 24. And here we have basically a black body curve with a few lines missing. In other words, this is an absorption spectrum with a black body curve. And we've got 1, 2, 3, 4 absorption lines. The first question asked is, well, what's the surface temperature of the star? Here we have to invoke Wien's law that says basically that the temperature of a star is equal to the constant divided by the wavelength that has the maximum intensity. Now, if we read off the graph, we can see this is approximately this value here, which I'm going to suggest around 490. So I get 2.898 by 10 to the power of negative 3. I divide this by my 490, but remember this is in nanometers, so I have to multiply this by 10 to the negative 9, and I get an answer of 5,914 Kelvin. Part B. We've got the absorption line W originates from an electron transition between the 2nd and 6th energy levels, and we have to use the Rydberg formula to calculate the frequency of the light absorbed to produce the absorption line. Well, first of all, we need to know that when we work out 1 over the wavelength, we can now substitute in our values, and so what we end up is getting it's equal to the Rydberg constant multiplied by 1 over 2 squared minus 1 over 6 squared. Now when you calculate that out, you're going to get 2437778 per meter. But if we remember that our c is equal to f lambda, then f is equal to c over lambda. Well, that's our inverse right there. So basically we just take this number and multiply it by the speed of light. So I'm going to get 3.00 by 10 to the power of 8, and I multiply this by the inverse of the wavelength, and I'm going to get the answer of 7.31 by 10 to the power of 14 Hertz. Question 24, part C. It says explain, so that's cause and effect, the physical processes that produce an absorption spectrum. Now, a diagram here would actually be very helpful. So let's say we have incoming light over here, and we have a cloud of gas here, and it's predominantly going to be hydrogen if we're using the astronomy example here. What are we going to produce? Well, the incoming light, of course, will produce a continuous spectrum. But what is happening here in terms of the hydrogen? If we take a hydrogen atom and actually were to draw its discrete energy levels, and let's say I'm going to draw one more here so I can use the Balmer lines. We have an electron here in the second shell jumping up to the third shell. Therefore, it absorbs a very specific wavelength or frequency. That electron almost immediately drops back down again and therefore releases a photon whose energy is equal to HF, again a very specific frequency, and they're exactly the same frequency. So what we end up having is these photons that are being emitted, but it's only those specific frequencies or wavelengths in a random direction. In fact, the vast majority of other photons that aren't being absorbed will just pass straight through. And so what we end up having is a continuous spectrum with characteristically missing lines, and as a result we get an absorption spectrum. Question 25. The mathematical below shows the relationship between the orbital radius and a satellite and its period. And considering the gravitational force, show how this model can be derived. This is a great example where you have to derive an equation that is actually in the formula sheet. And ultimately you can derive it using 3 different formulas. The first is V is equal to 2 pi r over t. That is, the circumference divided by the period gives us the velocity. The second is the force due to gravity, and of course that is equal to g big M little m over r squared. And the third is the centripetal force, which is mv squared over r. Now if you combine these two, and that is, you're saying that Fg is equal to Fc, what we end up getting is g big M little m over r squared is equal to mv squared over r. If you rearrange this, you're going to get v is equal to the square root of g m over r. Now this v here is that v here. So what we can do is square both and then equate them. And so what we get is 4 pi squared r squared over t squared is equal to g m over r. If I now rearrange this, I want r to be my r cubed over t squared to be my subject. I'm going to get r cubed over t squared is equal to g m over 4 pi squared, and we've derived Kepler's third law. Question 25, part B. A planet with 5 moons is discovered, and the following graph is produced from the observations of the orbital radius of the moons and their orbit periods, measured in the Earth days. It says calculate the mass of the planet, and we have to use the graph. Well, the good thing here is that if you look at the slope in essence is t squared over r cubed. So in other words, if we determine the slope, we can determine the mass of the planet, because if t squared over r cubed is asked for, we know that is 4 pi squared over gm. Of course, this is just inverted from our Kepler's third law situation. So what we do is we determine the actual slope. Now, I'm going to choose a value, and I'm going to choose this value right here, and I'm going to choose this value right there. Now, what that means is I will get a slope equaling to 0.32 minus 0.08. Now that's our change in y. I have to divide this by my change of x, which is equal to 400 minus 100. But I have to be careful here. These are non-SI units, and actually it's not even allowing for the square and the cube relationship. So what I need to do first and foremost is change this from days squared to seconds squared. Well, I just write down the number of seconds in a day and I multiply that by itself because it needs to be squared. Now down the bottom, it is already 10 to the power of 12. So I'm going to have 10 to the power of 12 here. But I also have this in kilometers. So I have to multiply this by 1,000. So it's 10 to the power of 3. But of course it's cubed. So this has to be cubed again. And so now I get a calculation for the slope and it equals 5.97 by 10 to the power of negative 15. Now, we know that this is equal to 4 pi squared over gm. And so what we have is 4 pi squared over gm is equal to this value here of 5.97 by 10 to the power of negative 15. I now can rearrange this. So I end up, if I want the mass, I have 4 pi squared all over my slope, which is 5.97 by 10 to the power of negative 15. But I also need to have my gravitational constant, which is 6.67 by 10 to the power of negative 11. And therefore, my final answer ends up being 9.9 by 10 to the power of 25 kilogram. Moving to question 26. It says muons are unstable particles produced when cosmic rays strike the atmosphere. The muons travel downward perpendicular to the Earth's surface at almost the speed of light. Classical physics predicts that they will decay and therefore they won't have really enough time to reach the surface of the Earth. Now, it says explain, cause and effect, qualitatively why these muons can reach the Earth's surface regardless of whether their motion is considered from either the muon's frame of reference or from the Earth's frame of reference. Let's draw a diagram to explain this. So here's my Earth's surface and here are my muons being created with a particular speed, and let's say it's at 0.98 the speed of light. Now, two things first. First of all, the muon's half-life, of course, is our stationary frame of reference half-life, of the mean half-life being 2.2 microseconds. Now, what means that the muon experiences that, but we, observing them traveling at close to the speed of light, will see a dilated time. That is, it's an increased time. So the words that the half-life of my muon is going to be dilated from our perspective. And so as a result, they are ticking slower. And so therefore, we'll have more time to reach the surface of the Earth. And therefore, according to the experiment, we'll be able to detect far more than we would if we would just use classical physics. So there, by observing the muon's half-life from our perspective, their time dilates, and therefore we can explain why more reach the Earth's surface. But we can also flip this. Imagine the muon is able to experience the atmosphere distance that it has to travel. Its half-life is the normal half-life of 2.2 microseconds. But the universe, the atmosphere, is racing towards it at close to the speed of light. So the distance it has to travel, let's say it was 10 kilometers, is no longer 10 kilometers. It's now a length contracted value, a much shorter value. So we have our length as a result being contracted according to the muon. Now the half-life is still normal, but the distance they have to travel is now shorter, and so as a result they can actually make the distance and therefore be detected by the detectors on Earth. And that's what you need to do to talk about both of those in order to get the 3 marks. Question 27, and this deals with the standard model. We are interested in a particular process where a proton collides with its antiparticle or an antiproton to produce 3 pions, a pion plus, a pion naught, and a pion minus. And we're given the information of the particles in terms of their rest mass in mega electron volts per c squared and their overall charge, and we're also given the charges for a number of types of quarks and antiquarks. The key thing to remember here is the composition of our proton and our antiproton to answer the first question, which is to identify the quarks present in the pions. Now, our proton is made up of basically 2 ups and a down. And that makes sense because our up is 2/3 and our down is -1/3, and of course that gives us a grand total of +1. Our antiparticle is going to be our anti-up, and our anti-down. And this, of course, flips the charges here. So we get negative 2/3, negative 2/3, and positive 1/3. And that gives us the reason why we get -1. That's not our question, of course. But we are knowing that these two combine in such a way to produce our pion plus, pion minus, and pion naught. So let's start first of all with the pion plus. We want a plus value. Now that plus value can only happen if I have 2/3 of our basically normal matter and a positive 1/3 of our antimatter, which basically means I have an up and an anti down, and there's our pion plus. What about our pion minus? Well, our pion minus can only be produced if I have a negative 2/3 and a negative 1/3. It can only happen if I have the anti-up particle and a normal down particle or quark. That means we now have used an up, a down, and a anti-up and an anti-down. If we look what we have, all we have left over is an up and an anti-up. Now, of course, these are opposite in charges, so we're going to get our charge being equal to 0, and there's our pion naught. Now, some of you might argue, can we have a down and an anti-down? That would also give us naught or a 0 charge. That is true, but we don't have any more quarks left to use, so this is the only answer we can provide. Part B, it says the energy released in the reaction is shared equally between the pions. Calculate the energy released per pion in this reaction. Well, we just need to look at the energy before and the energy after. So if we look at the energy before, what we end up getting is 940 plus 940, which is, of course, equal to 1880. If we look at the after, we have 3 pions, so therefore we have 3 by 140, which of course is equal to 420. So therefore, we have a difference in energy, and that energy goes to the kinetic energy of each of these pions. So now all we need to do is subtract the two, and we get 1460. That's our change in energy. Of course, this is shared equally, so now what we do is we divide this by 3, and so as a result, we get the energy per pion equaling 486.7 mega electron volts. And now we come to part C. It says the calculation of the pion's velocity using the classical physics predicts that each pion has a velocity, and that relative to the point at which the proton-antiproton reaction occurs, which exceeds 3 by 10 to the power of 8 meters per second. Well, why is this a problem? Well, first of all, is that special relativity states that c is a constant value. That is, it's the fastest speed in our universe, and only objects without mass can travel at the speed of light. All objects with mass can only travel up to the speed of light, but not including the speed of light. And so there's a problem. It can't certainly exceed the speed of light. Now, the way we resolve this is that when we look at the energy of our pions, the kinetic energy, that is actually a function of its momentum. Now, normally classical physics suggests that momentum is simply equal to mv, but that actually is not the correct formula. This only works for low velocities. So the correct formula is our dilated momentum formula. That is, P is equal to mv, where v here is the velocity at which it's going, divided by the 1 over v squared over c squared. So the momentum will dilate. That is, the momentum will approach infinity as it approaches the speed of light, but it'll still be under the speed of light. So using the correct understanding of momentum and therefore understanding of energy, we can actually determine the velocity of the pions to be less than the speed of light, because we are accounting for special relativity. Our next question is again a long response question that is being divided up into multiple sections. It says an electron gun fires a beam of electrons at a particular speed of 2.0 by 10 to the power of 6 meters per second through a pair of charge plates towards a screen that is 30 millimeters from the end of the plates. And there's a uniform electric field of 1.5 by 10 to the power of 4 newtons per coulomb. We're given also the width and the fact how far they are apart. And we know that the electron enters the beam midway. It says ignore gravitational effects on this electron beam. The first question is, show that the acceleration of the electron between the plates is 2.6 by 10 to the power of 15. Well, this is relatively straightforward. We know second law said the acceleration is equal to the net force divided by the mass. But of course, the force on a charge in an electric field is equal to EQ. And so we can divide this by the mass. Now, our electric field is provided. Our charge, of course, being an electron, like so. And we divide this, of course, by the mass of the electron. And you end up getting the answer of 2.6 by 10 to the power of 15 meters per second squared. Let's have a look at our next section, part B. It says, show that the vertical displacement of the electron beam at the end of the parallel plates is approximately 8.1 millimeters. In essence, this is a projectile motion problem. So let's have a look at the horizontal and the vertical. I'm going to put it over here. So let's look at the horizontal first, and you'll see why, and then we look at the vertical. Because the time the particle reaches here is the same as the particle at which it goes down. So we're ending actually up with a projectile motion problem. Now we know that the velocity going into the field is 2.0 by 10 to the power of 6 meters per second. We know the displacement here, and that's equal to 5 millimeters, so it's 5.0 by 10 to the power of negative 3. And of course, we want time. Now, time, of course, is equal to displacement divided by velocity. So we're going to get 2.0 by 10 to the power of 6 divided by 5.0 by 10 to the power of negative 3. I'm going to get a value of 2.5 by 10 to the power of negative 9 seconds. Now the vertical. So let's do SUVAT. Of course, our acceleration is known. We had that a moment ago, and we can substitute it straight in. Our final velocity we don't know. Our initial velocity, of course, is 0. Our displacement, well, that's the one we're looking for. And our time, of course, is our 2.5 by 10 to the power of negative 9 seconds. And now all we need to use is we've got S, U, A, and T, and we can use S is equal to UT plus a half AT squared. Our U is 0, so we just can have half multiplied by acceleration, which is 2.6 by 10 to the power of 15, and then multiplied by time, 0.5 by 10 to the negative 9, and of course all of that has to be squared. Now, if we calculate that out, I'm going to get 8.1 by 10 to the power of negative 3, and of course that is 8.1 millimeters. Now the last part is how far from point X will the electron beam strike the screen? To help us understand this question, we need to understand the fact that this particle is now leaving here. Let's say this is here, about our 8.1 millimeters, and is now traveling in a straight line, because as soon as it's out of the field, it's going to hit the screen there, and that's the distance that we are interested in. And so you can see what we have is we have an angle here that we need to work out. Now that angle happens to be the angle at which the final velocity is as it leaves the beam. So to solve this problem, the first thing we need to do is actually work out the magnitude of the final velocity at that point that we just did moments ago. Our final velocity, y, is simply equal to u plus at, but u is 0 in the vertical, so we can just simply have at. Now acceleration, of course, was 2.6 by 10 to the power of 15. Our time was our 2.5 by 10 to the power of negative 9, and that gives me a value of 6.5 by 10 to the power of 6 meters per second. Now remember, this particle, this electron, is leaving horizontally at 2 by 10 to the power of 6, and it's moving vertically at 6.5 by 10 to the power of 6. So in other words, the angle at which it is going can be determined by saying the tan theta of that angle is simply the opposite over adjacent, so we end up getting 6.5 by 10 to the power of 6 divided by our 2 by 10 to the power of 6. And of course, I can remove this, so all we get is 6.5 over 2. So tan theta is this value. And that's important over here because here it is now traveling at a constant velocity at that angle. before it hits the screen over here. Now we've already got 30, so what we can say is that angle here, right there, is going to be determined the opposite over adjacent. So this opposite that we've just determined, which is going to be our distance that this drops by, is I'm going to call this our value of y dash divided by the adjacent of 30 millimeters, 30 by 10 to the power of negative 3. Well, that's tan of the angle, but we already have the tan of the angle, and that's 6.5 over 2. You can see we can now work out what that y dash is. That y dash of a drop is simply now 9.75 by 10 to the power of negative 2 meters. So that's how much it's dropped by. But remember, it's already dropped 8.1 millimeters below x in the first place. So therefore, the distance we want from x is equal to our 8.1 millimeters, that is 8.1 by 10 to the power of negative 3, plus our 9.75 by 10 to the power of negative 2 meters, which gives us a grand total of 10.06 by 10 to the power of negative 2 meters, or what you can say is approximately 10.1 centimeters. Question 29. And here we're dealing with a situation where we have the force between two conducting wires, or wires with a current. However, this is a little different. First of all, is that this is connected in such a way so that both rods move apart. As you can see, A moves away and B moves away, but B moves further away. But we have a couple of conditions we have to pay attention to. First of all, there's clearly a repulsion between the two. But secondly, we are told that the currents are different in between the two. So how is that possible? Well, the way to do this is to ensure that the currents are moving in opposite direction. That will produce a repulsion between the two rods. And secondly, to have different currents, they've got to be different circuits. So the way I would connect it is this. I would start here with the negative terminal and connect this up like so. And then I would return this all the way around to connect it to the positive terminal. That gives me a direction of the current, in this case, in that direction. And now I connect the other one up too, but I want to connect this positive wire first to B first. Then this goes across. I do a line that sort of jumps so it's not touching over on the other side, and come back all the way to here. That, as a result, causes a current now in the other direction. But because they are two different rods, they will have different resistances in order so that they have different currents, because they're connected to the same voltage supply. But these currents are now in opposite directions and allows for them to repel each other. And that's, of course, because the currents are in opposite direction. So that answers our question part A. But part B says, when the switch is turned on, the current in A is greater than the current in B. Consider this statement. Position 2 results from a larger current in A, causing a larger force to act on B. It says evaluate this statement. Well, let's have a look at it. What determines the force between two current-bearing wires? And that is this law. The F over L, that's force per unit length, is equal to mu naught over 2 pi multiplied by the product of the currents divided by the distance separated between them. Now, this is a mutual force. It doesn't matter which is I1 and I2. In other words, this is consistent with the third law. That is, the force of A on B must equal the force of B on A. This is an example of Newton's third law, and you'll get I1 and I2. They're going to be the same value regardless of which one you use. So in other words, it's incorrect. It's not a larger force as acting on B simply because of the currents, because it's Newton's third law says it's the same. What is different, however, if, for example, one moves further away, so B clearly has moved further away, it means that B's acceleration is greater than the acceleration on A. And the only solution, therefore, if they have exactly the same force, is that the mass of A is greater than the mass of B. That resolves that particular problem. So we've evaluated the statement to say it's wrong, and we're using relevant physics can actually explain what's going on here in terms of Newton's laws of motion. An object sits on the floor of a hollow cylinder and rotates around an axis as shown. The cylinder rotation causes the object to undergo uniform circular motion. Now it says explain the effect of all forces acting the object if the period of the cylinder's rotation is halved, and it says ignore the effects of friction. Now one just little caveat here is that really for this to work there's got to be some friction here, but we are set to ignore it. So really the only forces we can be talking about are the two forces of A, the force due to the gravitational force sitting down on the floor, and then of course there is the force acting inwards, which of course is the centripetal force, and of course the centripetal force is equal to mv squared over r. Now it says explain the effect of all the forces acting on the object if the period of the cylinder's rotation is halved. Well, let's start with the period, shall we? So we know that v is equal to 2 pi r over t. So, in other words, the velocity that is here will result that if we increase or decrease the period, halve the period, in other words, if the period is divided by 2, the net result is that the velocity is increased by a factor of 2. But, of course, the centripetal force is proportional to v squared. Therefore, the centripetal force is going to be not 2 times greater, but 4 times greater. So therefore, the new centripetal force is going to equal 4 times the original centripetal force. But we must talk about the gravitational force. Well, the gravitational force, of course, is acting directly downward, perpendicular to the centripetal force. So therefore, there is no change in the gravitational force. It's still acting downward. The rate or the period of the situation will not affect that particular value. And now let's have a look at question 31. It says a thought experiment, a projectile is launched vertically from Earth's surface and its initial velocity is less than the escape velocity. Now the behavior of the projectile can be analyzed using two models, model A and B. And we're basically ignoring the Earth's atmosphere and any rotational motion or orbital motion as well. And we're asked to compare the maximum height reached by the projectile using each model. And in your answer, describe the energy changes of the projectile. Now, being a 4-mark question, I don't think this requires a big calculation to work out the two differences between the models. I might refer to it as we go along. But the first point here is that we have a uniform gravitational field, and what that means is that G is constant. Whereas in this model, we have a radial field, which means that the value for G decreases as you go out. Because the value, of course, 9.8 meters per second squared is the value we have here on the Earth's surface, but it progressively gets smaller because of the strength of the gravitational field. And you might remember that if we use the gravitational field formula, we get G is equal to capital G m over r squared. So in other words, the further it is away, the weaker the value for G as a result. So it says now compare the maximum height. Well, in terms of model A, what we're doing is we're giving it kinetic energy. And as we throw it up, that, of course, kinetic energy starts to decrease and converts into gravitational potential energy. Now, in terms of model A, the way we work this out, due to conservation of energy, we say that the kinetic energy is equal to the gain in gravitational energy. And so, as a result, what we get is equal to a half mv squared equals the gravitational change, which is mg delta h. And so you can see our height is determined really, if we cancel out v, by the fact that our change of height is dependent simply by v squared over 2g. But remember, this is assuming that g is constant. But what if I, for example, have a situation in model B? In model B, we have the same story. We have a kinetic energy, we give it, and that kinetic energy decreases as a result, of course, as it goes up. That, of course, converts into gravitational potential energy, or a gain in gravitational potential energy. And so what we have is, to have that gain, we have our delta U and K, but in this case, we have a half mv squared, and now our delta U is actually equal to G capital M lowercase m over, now our gain is our final minus initial, so our final minus initial becomes our R plus our H minus our initial, which is going to be negative G big M little m over R. And so that's going to be our gain as a result. Now, what this means is that as it goes higher, the amount of energy it has is now converted into a value for its potential energy that is a result, a different value, a smaller value than if we were to use model A, where G remains constant. And so in other words, as a result, with B, it is able to go higher. So I've discussed the fact that in B, it's higher than in A, and I've addressed the comparison there, and I've used the idea of kinetic and potential energy to explain that. Question 32, I'm not going to go into full details. It's a long 8-mark response, and this is really a great question where you are, in essence, showing what you understand. And it asks experiments to explore the interaction of light with matter. Now, there are a number of situations that we used in the HSC program where we have an interaction between light and matter. In any case, we have to show how this evidence from at least 3 such experiments have contributed to our understanding of physics. So let's talk about, first of all, the really obvious ones. We know that light interacts with matter in such a way that it shows that it has wave-like properties. And there are 2. We can talk about the double-slit experiment. And of course, this is all about diffraction and interference. Now, I'm not going to outlay here all the details required for the full A marks, but I would certainly be suggesting that the fact that we've got interference patterns suggests that we have a wave-like property in terms of the light wave. So in other words, the double slit experiment, where light interacts with the slits or diffraction gratings, which is matter, obviously shows that light has wave-like properties, and therefore we can calculate things such as wavelength. You can also talk about polarization. Now, polarization is again interaction with matter. Light, which is unpolarized, can pass through a polarizer, which is basically made up of a material that only allows one polarization axis to pass through, and using 2 different polarizers, you can effectively cut out the intensity. Now, again, you would elaborate on this, but the key thing here is, if you talk about polarization, you might talk about the intensity being I max multiplied by the cosquared theta. You'd provide the details, but in essence, it shows wave-like properties. This can be properly explained if you understand light as a wave. So these are both what I would say as wave-like behaviors that you can use. So there's already 2. Then, of course, we can talk about the photoelectric effect. Now, the photoelectric effect, of course, is where light strikes a metal and photoelectrons are emitted. And of course, we remember the formula that E max is equal to HF minus phi. We've seen this in a previous question in the multiple choice section. And it can only be explained by understanding that light can arrive and be discrete. That is, arrives in packets of energy or photons whose energy is equal to HF. And again, you need to elaborate on the photoelectric effect, the fact that if we increase the frequency of our photons, therefore we're increasing the energy, and that increases the kinetic energy of the photoelectrons. However, if we simply only increase the intensity, we're just increasing the number of photons, and so therefore we're only increasing the number of photoelectrons being emitted. And you need to talk about that. So there's 3. But could we have a 4th? Because it seems to suggest that there's more than 3. And yes, and that is spectroscopy. How that as light passes through a gas, then the atoms or the electrons in the hydrogen atoms absorb the energy and jump electron shells. In other words, it shows that light again has discrete properties. And of course, they're re-emitted, and then as a result, they go in different directions. But the thing is that the spectroscopy not only therefore provides evidence for the expansion of the universe, which we discussed earlier, but for example, we use the same process by understanding the chemical composition of stars and nebula and galaxies as a result, using our understanding of the spectroscopy, how light interacts with matter, with gases, and therefore allows us to identify not only, for example, the composition of stars, but also the density of stars, and of course, not only the inflation or the recession of velocity, but for stars themselves, the fact that they are moving away, moving towards us, or spinning, for example. So as a result, there's a series of experiments that relates to our understanding and our contribution of our understanding of physics. And lastly, this question 33, and it's a 7-mark question. And we have a pendulum that's swinging over a fixed cylinder that can rotate. And we are asked basically to analyze the motion and energy transformations of both the can and the magnet. So let's break this down. First of all, this is a pendulum. So it starts off here with a certain amount of potential energy. And of course, as it swings down, it has a certain high degree of kinetic energy. And of course, over here, it has a high degree of potential energy. In fact, it stops here, so there's no kinetic energy at the ends. And over here, if we mark this to be our zero line, the amount of gravitational potential energy from this point is in fact zero. And so we've now already started talking about the energy transformations of our pendulum. That is, it goes from gravitational to kinetic to gravitational potential energy. But it's a magnet, and the magnet passes over our cylinder here. So what does that do? Well, first of all, the magnet has a magnetic field, and this particular cylinder, being a metal cylinder, it's an aluminium can, or as a result, will actually experience a rate of change of flux. So what we end up getting is that as the velocity increases towards the can, we end up getting a increasing rate of change of flux as a result as it moves towards the can. And this, of course, leads to the idea of Faraday's law. That is, we're going to generate an EMF, and that EMF results in eddy currents being produced in our metal over here in our can. Now, of course, those eddy currents, as a result, will produce a magnetic field that opposes the one that causes it. So that is automatically Lenz's law. And so therefore, if the north approaches here, we're going to produce a north pole at this edge of the can. So the can initially is stationary, but because of the repulsive effects of this north arriving to this induced north over here, the can will now start to rotate in a clockwise direction. And of course, as it passes over, that is similarly speaking, of course, as the south reaches this side, we're getting a current over here. And of course, as this moves away, as the south moves away, we're going to produce a pole on the other side, but this time it's going to attract it, and as a result, the same principle, it pulls the can again across. But of course, as it moves away, that can is going to have some momentum in terms of rotating, but the effective amount of force that it experiences due to this electromagnetic effect is reduced because it does move away. But of course, that means that we have now kinetic energy in our can because our can is rotating. Now what happens? It returns. Now, because the can is rotating in a clockwise direction, as it returns, the same effect applies. That is, as the south approaches, we're going to produce a south pole due to the eddy currents produced again by Faraday's law and Lenz's law. That will apply a force in the opposite direction. So now the can will stop, and as a result, we'll have kinetic energy equal to zero, but then of course it will start to rotate. So then the can will actually start to rotate. In this case though, in a counterclockwise direction. Now I say counterclockwise, so that if I write anti-clockwise, I write AC here, but obviously in the opposite direction. So what we have is, as the pendulum swings back and forth, it's a conversion of gravitational to kinetic. We also have a change in the can's kinetic energy as it rotates initially in the clockwise direction and then afterwards in the anti-clockwise direction. And of course, this repeats as it goes on. But hold on, we're missing one bit of energy, and that is the energy of the eddy currents itself. In other words, we have these eddy currents producing electrical energy as a result of Faraday's and Lenz's law. So we have a generation of energy there. So in other words, the energy of the system must include the eddy currents as well. And how does that affect the system? Well, the fact is that these eddy currents aren't going to go forever. They're going to slow down, and so they're going to heat it up. So as a result, you're going to find that the pendulum will actually start to slow down. The actual fact, as it moves away and as you have this attractive force, the pendulum slows down. Now, if it slows down, then the amount of total energy, mechanical energy it has, is starting to decrease. But that gets transferred or transformed due to the eddy currents and the heating effect that's going on. In essence, what you're getting there is electromagnetic braking. And so as a result, eventually the whole system slows down. What you're having is that you have a drop in overall mechanical energy combined of the pendulum and the can that is rotating backwards and forwards as a result. And of course, the can starts to get warm. And so we have heat energy as our final energy, which of course then dissipates and is not reclaimable. And so that is what you would need to do for question 33. I hope that has helped you understand the short answer section. Please like, share and subscribe. My name is Paul from Physics Bye for now.